Okay, so I think you can see this screen, hopefully. Um, so this is the backpropagation algorithm. I think it actually helps a lot. We do this sometimes in tutorial to go through the actual slides, well, the walkthrough by another person outside. And so let's go do that. So have you guys seen this tutorial? So it's a little bit easier to go through what's happening in this network. Okay, so that you can go through it. So I'll just put this in chat and then feel free to follow along there. Where's my chat window? Chat. I threw it away, okay. Okay, and so you can follow around along the architecture here so that you can see what's going on. Okay, so this one isn't as complicated as the one that you asked about with 2 hidden layers, but I think the mechanics are pretty much the same. Okay, so let's just go through this, and if there are additional questions, we'll come back to that in a while. All right, so hopefully when we walk through this, most of you will be understanding about what's going on. Okay, so as you saw in the slides earlier, right, you are clear about it. What happens is we generally do a feed forward pass first, right? So we're going to go through the network and calculate from the actual examples, right? Okay, from the actual feature values here. Okay, and we're just going to push it through the network, okay, by just calculating all of the operators, right? Okay, until we get to the end of the network. Okay, and then once we've gotten to the end of the network, we will have computed some value. Here you can see it's computed, 0.73 as a function of all of these inputs, right? The inputs are x values. Our current parameters are the thetas, right? So we have the thetas for each of the edges here coming in. And basically, what we want is to decide whether this value is the right value or not, right? So there's some loss that might be generated if this value that is passed through is not the correct one. Okay, so then the next part, what we're going to do is then say, okay, maybe we don't have the right value, right? What we want to do is figure out the right value, what the right value should be. So I'm going to take a look at the loss, right? So given the gradient that's calculated, I want to know how to adjust the parameters that we have here, right? I need to be able to adjust these parameters given that, right? So what we're going to do is calculate the deltas for all of the nodes in the network, right? The thing that happens after each of the outputs going through, right? So delta, and delta here, right? And these will help us know how to change the parameters, right? As you saw in the lecture, once we have the delta operators, we can just do one single back propagation pass, right? To start from the top, which is our ultimate layer, right? And then recursively go backwards to calculate all of these. And I can know how for every single weight, how it should change in order to get these two values to coincide properly. Okay, so let's see how that works on this the other side. Okay, so the initial weights and biases we have here. Okay, here's our bias right down here, and our weights that we have, all of them are in red, right? And the training inputs as located on this are 0.05 and 0.1. Okay, and then I'm just going to do the forward pass on this to calculate all the weights. So if you do this, you can just go through all of the things here, right? So basically, it's just going through the network and calculating all of the values, right? So at the end, after I go through all of the functions here, I will get this value. And then I have to put it through the logistic function to get an output because here I'm using a logistic function as the last out, right? So that's the final output that you see coming out at both of these layers right here and here. Okay. Okay. So yeah, so you can see there's two outputs here, as it says out one and out two. Okay. And I get these values for both of those. Okay. Now I'm going to go calculate the total error, right? Using squared error for both of these, right? So here I have the actual target. So let's say the target for O1 here, right, is 0.01, and that's saying that the other one is supposed to be 0.99. Okay, then I can calculate the squared loss, right, as these values. Okay, that's just applying the error, right? So then I have the total error that I have, and then I need to pass that backwards because I want to get my E total down. I want to change it so that it works well with a new set of weights. Okay, so if you look at the network, right, let's take a look what it says here. Consider W5. Okay, so let's go back to what the network says. Okay, so W5 is this node up here. Okay, this one up here, right? And so we want to know how it's going to change. And if we can change this one properly, then maybe we have a method of changing the other ones that are farther down in the network, right? Closer to our individual inputs. So it's a recursive strategy where we talk from the penultimate layer to all the way towards the front, right? Back propagating, right? Okay. And so what we are basically doing is just doing the chain rule, right? So we're looking at the error that we have at the output, okay? And then trying to decide how it gets changed by the nonlinear activation function, which is how we get from the net to the out, right? And then from there to see how it is going to be affected by the input weights, right? So we have two inputs, H1 and H2, and I have a bias that's 1. And then I have two weights and one bias, right? Two weights and one bias here, right? With W5, W6, and bias 2. Okay, and basically when we do this by the chain rule, basically we can see what's going on for W5, right? So when we think about W5 here, it's basically trying to look at the partial differentiation of the total error, right? The total error as a function of how we can change W5, right? So when we write out the chain rule, all we need to do is look at all of the edges and connections, operations, multiplying them all together using the chain rule to get that one piece of information, right? So when we look at this, we can decompose it. I have a total error, okay, and W5, and then intermediately, I have the activation function out O1, which is over here, right? And I also have the net input. This is our signal, right? The signal that's being accumulated here, our S, right? And these two things are being done together, right? Okay, so I have all these partial differentiations and I can just multiply them together to get how the total error is changing with respect to the changes in W5, okay? That's what we're doing. Okay, so let's take a look at this, right? If we look at W5, which is at the top of the network, right? The bottom of the network is not affecting anything at all. So even though there's an O2 for out 2, okay, that's not connected to the network for W5, right? Because W5 was somewhere up here, okay? It's connected to our out 1, okay? But our out 2 doesn't get to it. It affects the other node over here. Okay, so it will make some changes over here, but it doesn't change W5, right? So that's why this part is discarded, okay? We don't care about that. Okay, it's respect to the total loss, right? Which is why we had to add the error coming from both this one and this one together. Okay, but you can see that if I change anything on this side, if I change the weights over here, it won't affect anything on W5, right? Because W5 is only changing the outputs that's associated with out one, right? Target O1, right? This term here. Okay. Okay. So what we're doing is just looking at how it changes with respect to that input, right? So we said in the beginning of this problem, if you looked at the beginning, it just says all of the units are using the logistic function, I think. Okay. So we have to take the derivative of the loss with respect to this operator, which is just telling us how the input of O1 is being affected with respect to the net, right? This is the signal. So let me use a different color for that. That's our signal, right? So I need to be able to calculate this. And it's the same as what we saw on the lecture slide. So if you go back to the lecture slide, right, and we did the backpropagation for this one, okay? We are basically doing exactly this operation, right? This is the same logistic operator, right? So we're just stepping through all of these steps here and trying to use all of these equations over here, right? These are the, your calculus equations for derivatives. Just now we're doing partial derivatives, so no different, just we're looking at one variable at a time, okay? So when we do that, you can calculate it, right? So you can do it directly as the compositionality of the logistic function is illustrated, right? And do it using this equation here, which is the g of s times 1 minus g of s, right? That's the logistic function derivative. And then we'll get the value, right? So we just take the output that we got. This was our actual number that we got for the loss of the out. Okay, we take and its derivative, and then we'll get this new value, right? So this is the amount of way that O1 is changing with respect to its input, right? Exactly as the partial derivative says here. Okay. Everyone following that so far? So if you are or you're stuck, let me know. You can write no if you're not getting it. If you are, that's great. Right, so we're basically just trying to figure out each block individually, right? Because as you saw at the beginning of this chunk, okay, here, all right, we're looking at that specific neuron output, okay? If you can, for a second, remember this diagram, okay? Okay, and square it away with what you saw up at the top, right? Which is basically focusing in on this part here, okay? Right, just this part here, right? So I'm just saying that there's three operations, right? There's a total loss, there's the out, and then there's the actual weight. So there's three parts, three components that are being taken into account, okay? Just for W5. Okay, so that's what we saw here, right? So now we're computing all of those values, right? And then we would have eventually gotten our output for all of this, right? So here it is, okay? I just have these three partial derivatives all separately calculated, okay? Because I calculated each of those components separately, right? I took the input of one and did the partial derivative, okay, and I came up with a value for it. So I'm just going to plug this guy into its respective part, okay. So I'm doing that. Then I can get finally using the chain rule. I have three different parts here, so I'm just multiplying all three of those. I get the partial derivative of how the loss is changing when I tweak W5, right? I move it up or down a little bit, it will change, right? Okay, so it says here, there's a partial derivative in the positive way. So if I change W5 up, the loss will go up. Since I don't want the loss to go up, I should change W5 down, right? So the magnitude of the number tells me how much it's going to change. Okay, so in the slides, okay, earlier, I think in the backprop part, okay, we said we want to calculate these deltas, right? The deltas allow us to compute all of the weight changes all on one backward pass, okay? So separately, if I think about a particular part of the network, let's say this weight here, okay? I would need to get all of the information that happens upstream as well as how it's being dependent on downstream, which means to calculate that one node's weights, I would need all of the information about what's happening up here, okay? So it's a lot of computation. But what the delta rule is saying is that if you have these deltas, we are basically doing some like dynamic computation, right? Dynamic programming, where when we find these delta values, they're going to be applicable for everything downstream, closer towards the front. So when I compute the deltas, I'm actually solving simultaneously all of the partial derivative and changes that I need to make for all of the weights simultaneously, which is great. Okay, I don't have to compute a separate set of partial derivatives for each branch, each path through the to the network. Okay, I just do one uh, pass from the back towards the front and calculate all the deltas. And then these deltas are basically the chain rule embodied, right? For those free products that we just saw, okay? So as it says over here, you'll often see this calculation in the form of a delta rule, right? So that's actually what we wrote here, okay? This part down here. Okay, and let me scroll this up a little bit. Oops, wrong way. Okay, so this delta is basically saying, okay, how much is the output of one being affected by that particular weight? Okay, so I can then just times it by the out of that to get the delta for 5. Okay, so that's very nice. This is taking the last delta at the ultimate layer, the last layer that's easy to calculate, okay, which is what we showed you on this slide, right? Okay, just to say, when I have the actual last layer and I want to know how it changed with the information coming from the signal, right? Meaning from the actual output here and then going through the nonlinear activation function, if I change the signal, how much is it going to change my final loss, right? That's our delta rule, okay? So we combine two of the terms that we use to find how to change W5 into a delta, okay? Okay, that's what it says over here, right? So basically I have this delta, and that is telling me how I can change that. Okay, how is this useful? Well, it's going to be very useful when we get to another part of the network, like when you come to here, all right? So here is where the delta sits right now, this delta that we're talking about, okay? But you can see, for example, over here, the delta here, all right? It's going to be used for helping to compute information about how this weight is going to change and this weight is going to change, okay? And actually, once you know this delta, okay, I don't need to know anything about up here. I don't need it because it's all encapsulated by this delta, okay? This is all that I need to know, okay, to tell me how I need to change these two weights, because everything that I need to know about how to change the loss upstream, meaning farther up this way, is already encapsulated in the delta, okay, the delta that I computed, okay? So all I need is this weight, and of course I need the input, right? The input that I have coming out of this node and this node, okay, in order to know how to change W2 and W1. Okay, so that's the idea, is this dynamic programming idea, okay, that for every part of the node, okay, for every node in the network, I'm going to compute a delta, which is, whatever is in front before I accumulate the signal, right? And these are going to help me compute all of the other values, right? Because if I want to know, for example, how to change W4, all I need is this delta here. If I need to know how to change W6, all I need is this delta up here, right? Those are the only pieces of information that I need in order to get the right information to figure out what to change W6 or W4 for. Okay? Everyone clear about that so far? So again, tell me if I need to go faster or tell me if I need to go slower. by marking on your participants list. So I know you're following or not following. Okay, Akansha, Li Shuo is okay. How about the rest of you? Anyone not following? I'm really concerned about that. Okay, because almost always we have a backprop question. Yeah, I mean, yes, it's true, and some of our TAs have said this too. This is something like learning how to do arithmetic. I mean, you don't need to know how to learn how to do arithmetic. You can just use a calculator to do it, but it's helpful to know the mechanics of doing backprop. So we also will test you on this, even though when you use PyTorch or when you use TensorFlow, you never have to do backprop by hand, okay? There's a point, right? We program it so we don't have to do it. But just like data structures and algorithms, we still need to know the algorithms and how to execute it in order to do it well. Okay? All right. So we're all good so far. That's great. I haven't seen any no's. So if you are not sure, you can tell me, okay? I really want you to get this very clear. Okay, so let's do another harder pass, right? Let's look at how we're going to change the weights for W1, right? W1 is just like any other part of the network. Even if you do two-layer network, which we have done before in final exams, okay? So not having just two hidden layers or three hidden layers, the mechanics are all the same, okay? What we want to do is do the pass such that we can figure out how W1 is changing, right? W1 is changing. And I said the way that we're going to do that is by figuring out what the delta is here, right? If I get the delta here, then I know how W1 can change, right? But this delta is actually fairly easy. I just have to think about all of the other deltas that it depends on. So it depends on this delta over here. It depends on this delta over here, right? Because there's basically two outputs that are happening here, right? So that is the way that I'm going to calculate this. Okay, so as it says in the equation up here, right, when I want to look at how to change, right, the E total with respect to how I wiggle around W1, it's going to have these different parts, right? So I have the three different parts that I'm going to add together, okay, for the first chain, and then another three parts for the second chain. Okay, so we can do that. So let's step through here. Okay, so it says here, we are going to do a similar process as we did for the output layer, but now we have output for each of the hidden neurons contributing to the output, okay, for multiple output neurons, right? I'm just reading up here, okay? We know that out1, H affects both out at O1 and at O2, right? So that means when we think about H1, right, the weight that's associated with W1, then I need both of those things into account, right? So if you look at this, this is our H1, this one here, right? So that's what we were thinking about. Okay, so the two big blue arrows indicate how H1 changes the output of the final loss, right? Because the final loss is dependent on both the outputs here. So I'm going to need both of the blue arrows to compute H1. Okay. Okay, let's see. All right. So we are going to do the same things as we did earlier, right? So we have those parts of information. Okay, and we already calculated this part due to the delta times W5, right? The first delta in the first row. Okay, so we can get the output of those, right? And then we need to do the bottom line as well. Okay, so we can plug them in, and then we get how the error at what does that say? O1 is changing with respect to H1. So this is the top line, right? Basically for our O1 here, how's it changing with respect to, sorry, let's put the H over here, okay? So that's the first part, right? Now we need to do the second part. The second part is this bottom part, right? O2, and then how it's changing for that part. So we haven't done this part yet. Okay, so up to this point here in the red, we've just done the first branch. Okay, so yeah, this is this part here for H. Okay, Now, let's go and do it for EO2, which is the bottom branch, right? So we're going to do the same thing. It says at the bottom of the slide, right? So we want to follow the same process for E2. Let me change the color. Sorry about that. I didn't do that properly. Change color. Okay. So if I compute all of those same process, right, it's just another different delta that I have here, not the same one that I had before, and then multiply it times whichever weight this one is. So this is probably W7 or something like that, I forget. Okay, then I will get a similar value for how E2, which is the error on this one, is changing with respect to H1, this guy over here. Okay, so we're all following that so far? Is there a way to zoom in on the Zoom? Yeah, I think so. Let's see. So let's see. Yeah, okay, that's good. Is that better? Okay, so we can follow the math a little closer like this. Yeah. Okay, so then you will be able to calculate these two branches, right? So they're basically the same computation that you saw earlier, right? It's just that now we're putting them together, right? So we have the earlier, this was from the red branch, right? Our net output with respect to H1, right? And then we're doing the other branch, which we hadn't done before, but it's a very similar computation, okay, for the bottom branch for O2 with respect to H1, right? So this is here, which would have the same types of terms as this one, okay? It's just, it would be another set, right? A green set of terms, okay? There's actually three terms in there, but we combine two of them to be our delta, right? Okay. So then what we want to do is finally get the amount that we have aggregated for both parts, right? So that's what it says here. We have the losses for both E1 and EO2, okay, EO1 and EO2, again, with respect to the same guy, right, our H1, our aggregation of the signal, okay? And that is, of course, the same as having our E total, right? Because E total is the sum of these two guys, right, put together. Okay, so this is going to be our delta again, but it's the delta at the next level, right? One level down. So if you remember, our network looks a little bit like this. Cross, 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 and then out, right? Okay, so we have now using this guy here, computed exactly, and you can annotate yourself, right here, okay? That information that I need, okay? So then it says right here, right? Now that we have all of this together, I have my delta rule. I just need to figure out how to change my W so that it's going to change appropriately, right? And I do the same thing. I pass it through the activation function, okay? And then I will finish, okay? Then I have finished all of the computation when we scroll it down a little bit more. Come on, Zoom, go. It's a little laggy, sorry about that. So we have the total that we are getting from both sides, right? So this is just, let me move this up a little bit, okay? This is just saying that I'm going to go through both of the outputs, right? Both of the incoming outputs to my H1 and do the specific free terms for each of those. And then I'm going to go through the node itself, right? Which is these two parts, okay? And then when I have that computed, then that's it, right? I basically have my delta rule times the input, then I'm all good. Okay, so what you should do with this is just remember where the deltas are being placed, okay? Because basically when you think about this, all we want are to think about the deltas, right? So I have the deltas from the previous one, right? It's just that I am timesing it by the weight to get this value, right? This entire term is being encapsulated in the delta and refactored into my weight, okay? And then when I have that, because I have this delta for, again, each of the different nodes coming in, okay? I have a delta for 0, delta, sorry, let me call this delta for, let's see, out 1, right? Delta for out 2, okay? And then I'm computing this guy here, delta for H1, okay? So even if I were to have more downstream nodes here, right? The nice part is once I've calculated this delta value, right? I no longer have to care about anything on this side because it's already encapsulated, right? So if I want to, let's say, calculate how the weights are changing at the next level, I just take this one, times it by the weight, and I'll get a new delta over here, right? And then I don't need to care about this one anymore, right? So that's the nice part. We're just stepping down iteratively from the back of the network where I get my final loss function all the way to the front. And I'm just iteratively updating it. It's a partial ordering of nodes, right? And I'm just going to topologically sort them and go through and go through all the layers and update. Okay, so that's how we do backpropagation, right? So you can do this for all the other parts, okay? So you can see where we're going with this. I'm gonna zoom out a little bit. If it gets too small, let me know again, okay? So we'll repeat it for all the weights that I have here. Oops, how come it's not updated? Okay, here we are, okay? And then I can see what's going on, right? So if I change this way, this way, this way, this way, this amount, these amounts, right? I'm going to reduce my network error, right? So originally there were different values. I think they were like 0.2, 0.5, and 0.3 or something, okay? And then it got updated it a little bit, right? And it says here, when I do the forward pass, right? When I do the forward pass with this new values that I have here, all of these new values, okay, I will have reduced my error, okay, a little bit, okay, down 0.29, okay. So if we do this enough times and we keep on doing backpropagation, then we will find the optimal weights, right? It's basically doing this one linear pass through all of the nodes in topologically supported order, right? Where we take the most simple node is the one with no dependencies, which is usually the classification node. In this case, we have two outputs, okay? And then we're just pushing it all the way back through the network using one linear pass, one computation of delta for each node, okay? And then using that to recursively compute the rest of them, okay? And I do that for one pass, then I have updated all of the weights simultaneously. So even though there are lots of different paths through the network, there's exponential number of paths. Just using this one topological ordering, I've actually computed all of the correct weights. So it's a really, really nice algorithm. It's very simple. It's just calculus applied to neural networks. Okay, that's all you can think about it. Okay. Any questions from here? Okay, if you are not clear, I suggest going through this and working out the math in detail. It's not particularly hard, it's just tedious, okay? But I think this is a really good post because it goes through all of it. In fact, our tutorial pretty much covers this one, okay? But I've spent a little bit more time on it because I see that you guys are wanting to see more of the computations for backprop. Okay. So let's go to our things here. So again, if you have